Amir, Reza from, from Case Western Reserve University. He will talk about mutual information regularization for fair-aware deep imaging representations.
Thank you for the opportunity to present this work conducted at Case Western Reserve University. I'm Amir Sadri, and I'm going to present how we built a fairness-aware framework to improve both performance and equity in medical image analysis. So to introduce the concept, I'd like to start with the term fairness in my title. Fairness refers to disparities in medical imaging model performance across sensitive attributes such as gender or race, often driven by bias in data or training. These plots generated from the real model illustrate this point. The left plot shows how the model performs differently for male and female patients with a noticeable gap in AUC distributions. And on the right, you can see racial disparities. The model performs much better for Caucasians compared to the other two racial groups. Roughly speaking, over 100 methods have been proposed for dealing with fairness so far, but all can be categorized into two main different groups. The first is fairness evaluation, which focuses on post hoc assessment, identifying subgroup disparities to understand the nature and extent of the bias. And the second is fairness mitigation, which aims to actively reduce the bias within the model development pipeline. This includes pre-processing method that modify data to balance subgroup, post-processing methods that adjust model outputs, and in-processing methods that embed fairness constraints directly into training. Among these, in-processing methods tend to be the most effective for learning subgroup invariant representations without sacrificing performance. However, they can also add architectural complexity or training instability. This motivates the need for a more stable and effective in-processing approach for medical image analysis. Some limitations of prior in-processing approaches include being model-dependent. For instance, adversarial learning method attempt to remove sensitive information from model features, but they are often highly model-specific. Applying them to different tasks or modalities typically require substantial modifications to the architectures. Other approaches, such as disentanglement, risk removing information that is useful for main tasks, and their optimization processes are often less stable. To address these issues, we developed fairness-aware mutual information regularization, or FAMI, a generalizable framework for fairness in medical image analysis. FAMI is model agnostic and can be applied across tasks, modalities, and architectures. In addition, it achieves stable optimization, can be plugged into diverse architectures, including CNNs, transformers, and multimodal models, and avoids the instability of mutual information estimation. So in a general pipeline, the input image is fed into a model for processing and generating predictions. The model typically optimizes using a loss function such as cross-entropy during training via backpropagation. To incorporate fairness constraints, sensitive attributes such as gender or race are also considered. Our method builds on the fair prediction rule, ensuring that these predictions are independent of attributes. We achieve this by introducing a mutual information loss that minimizes dependency between the learned representation and sensitive attribute. The proposed loss combines cross-entropy for accuracy and mutual information for fairness. However, estimating mutual information introduces an additional challenge, as it requires knowledge of the underlying data distribution, typically unknown for real imaging data. And deep learning-based estimators often rely on approximations that can be noisy or unstable. Our solution is proposed FAMI method, which updates model parameters without explicitly estimating mutual information. Instead, it uses mutual information difference theorem to directly compute the gradient via a score function difference, or SFD. The idea behind our FAMI algorithm is that we have a sensitive variable and a model feature space. At the beginning of the training, there is a significant overlap, which represents mutual information, meaning that extracted features still encode information about a sensitive attribute. The goal of our method is to progressively reduce this overlap during training and breaking the link between them. By the end, there is little to no intersection, showing that the features are independent of the sensitive attribute. This is a core idea of our approach, minimizing mutual information to promote fairness without sacrificing predictive power. We also provided mathematical proof for selecting a proper learning rate to ensure convergence. We applied our method to two data sets. The first was a public set of 3,300 OCT images for glaucoma detection with race as sensitive attribute, and the second was an in-house data of 186 pre-chemoradiation MRI scans for rectal cancer, where the task was binary classification of pathologic complete response, or PCR, to chemo, with gender as a sensitive attribute. We applied our FAMI framework on two representative architectures, a vision transformer and a DenseNet. For evaluation, we used AUC to capture overall classification performance. And from the fairness perspective, we focused on metrics such as equal opportunity, or EOM, which specifically measures the balance of true positive rates across different subgroups. Here are the results. Starting with the AUC forest plot at the top, if we look at the glaucoma data set on left, the FAMI-informed vision transformer clearly outperforms the naive VIT model with significant improvement across all subgroups. That's what the different colors represent. Now looking at the EOM results below, where higher bars mean better fairness, we again see consistent improvement with FAMI. We also see a strong performance for both AUC and EOM for the rectal cancer data. For comparison, we also evaluated other fairness-aware methods that build on VIT, such as FairWidth, FIN, and FairBatch. As shown here, FAMI is statistically significantly better across both dataset and both metrics. And in the paper, we also showed that these trends hold when tested with other architectures like DenseNet. In both cohorts, we also used DenseNet to evaluate FAMI for finding the gradient of mutual information. To put it this into context, let us first look at two alternative approaches for estimating mutual information using deep learning architecture. The first is MIGE algorithm, and the second is MINE method. Here are the results. This is MIGE. It provides reasonable mutual information reduction, but shows fluctuations, especially in the later epochs. And this is MINE. The curve is noisy and unstable, which makes it less reliable. And this is our FAMI results. Notice how it converges smoothly and consistently with minimal oscillations. The stability is reflected in the lowest total variation and RMS values, showing both effectiveness and reliability. We presented FAMI, a fairness-aware regularization method that avoids adversarial training and instead backpropagates directly through the fairness term, making it simpler and more efficient. We incorporated stable mutual information regularization, which improves efficiency while maintaining reliability across the different datasets. And overall, FAMI achieves a strong balance between fairness and predictive performance across diverse medical imaging tasks, showing both its adaptability and robustness. Lastly, I'd like to thank everyone who helped this presentation happen. And thank you for the attention. I'm now ready for questions.